and it's everybody's business to know about space and space science instruments. Good afternoon, everyone. Here I am Sai Madhuri, welcoming you all to the 46th episode of our creative session. Creative thoughts makes us active. Activeness keeps us creative. So, together, creative and active, we are creative. And we are with a tagline Knowledge Square, which means knowledge is doubled when we share it. Creative is a group of people waiting with bated breath to gain knowledge, and scholarly people who are enlightened are with us to share their knowledge. Creative is a platform where knowledge is sharing by conducting online sessions in Zoom app and every Saturday. And we are live in our creative YouTube channel also. Today's session is about space science instruments, techniques, and challenges. To discuss this topic, we have Dr. Radhakrishna sir with us now. I welcome Dr. Radhakrishna sir on behalf of all the creative participants. Before starting the session, I welcome Miss Varshini from Mangaluru to introduce our speaker. Over to Miss Varshini.
Hello, good afternoon, everyone. Today I'm here to introduce a dynamic personality and today's center of attraction, Dr. Radhakrishna V. Sir. Sir is instrument scientist at Space Center Astronomy Group of UR Rao Satellite Center, ISRO Bangalore, and currently head of instrumentation division. I'm happy to share that Sir is from our Tulunadu. Sir completed his BSc from St. Aloysius College, Mangalore, and MSc in physics from Mangalore University. Sir obtained his PhD from Indian Institute of Science, Bangalore, in the area of applied physics and instrumentation. In the year 2003, before joining ISRO in the year 2007, Sir was postdoctoral fellow at Toyashi University of Technology, Japan, for 5 years. Sir research area mainly focuses on ionizing radiation detector, physics and instrumentation, and also microsensors. After joining ISRO, Sir is leading the team in developing instruments for space science experiments. Sir was PI for Chandrayaan-2 large area soft X-ray spectrometer payload development. Presently, Sir is PI for X-ray spectroscopy and teaming instrument to be launched on ExpoSat. Sir is also leading the development activities of future instruments like X-ray polarimeter for space astronomy missions. Today, Sir is here to share his experience, bundle of knowledge about the space science instruments, techniques, and also the challenges they had faced. I heartily welcome you, sir, for this enlightening class. Sir, நமக்கு class நடப்பதுக்கு வரல. Thank you.
Okay, thank you. Thank you very
Thank
much.
you. Thank you, Varshini, for the introduction. It's our pleasure to have Dr. Radhakrishna sir with us today. We are all ready to know about space science instruments, techniques, and challenges. Over to Dr. Radhakrishna sir.
Yeah, thank you very much. Let me share the screen first. Can you see that?
Yes, sir.
Hello, can someone is there? Can mute? Okay. So you can see the slides, right?
Yes, sir. Yes, sir. We can.
Okay. Okay. Thank you very much. At the outset, I would like to really compliment the creative team. I know it's a very unique name also, and also this your commendable effort in making these lecture series and other activities reach everyone who look for it. And thank you very much for this opportunity given to me to address you all. And thanks to Srinath and his team for this. And thank you also for the introduction you have given. Okay, so this is a lecture arranged at very short notice. In fact, just day before yesterday, Srinath asked me, so I just said okay. But the title, I was wondering what shall I speak on. So finally, I came to this space science instruments, space science instruments techniques, space science instruments techniques and challenges.
Sir, please unmute yourself, sir.
ಈ ಮೂಲಕ ವ್ಯಕ್ತಪಡಿಸ್ತಾ ಇದ್ದೀವಿ ಇದು ಡೆಮಾಕ್ರಸಿ now.
Yes, sir.
Okay. uh, yeah, so the title looks a little too technical: space science instruments techniques and challenges. Too technical, but let me assure you, I have kept it very general uh, way, so I am sure all of you will be able to appreciate at the end of this talk. So let me begin with the science missions, and we all hear about space science missions. We keep hearing about that. I'm sure all the audience here are familiar with some or other space missions, science missions rather, uh, which has been flown by several countries and agencies. So there are different types of science missions, like we have science missions for astronomy, that is to study celestial objects like stars, galaxies, etc. So we all know about Hubble Space Telescope, Chandra Telescope, Compton Gamma Ray Observatory, Spitzer. These four are called, NASA's four great observatories. So these observatories have changed the way we look at the universe. So it has vastly expanded our knowledge of the universe. And also, we have missions by ESA like XMM Newton, and then recent JWST. Uh, yeah, so JWST, that is flown, and then we have our own AstroSat, India's AstroSat. I'm sure most of you know about AstroSat mission. So like that, several missions we have seen, and then there are planetary missions, because uh, when you talk about space, it includes even our own solar system, and the study of planets in our solar systems. And there are several missions for this Apollo and Apollo. These are lunar missions, lunar landing missions, and then several lunar missions by various countries. And then we have Mars missions, and most of these are landers and rovers, and also many of them are orbiters. And then for solar science, we have SOHO, solar and solar observatories, solar dynamic observatories, Hinode. So there are several missions for doing solar science. Then we also know about the deep space missions like Voyager 1 and 2. Both of them have crossed our solar systems. So like this, we have seen several science missions, several are in the pipeline, and several will be flown in future. And most of the countries which are involved in these, like Americans through their NASA, and the European Space Agency, JAXA, that is Japanese, and then Russian space agencies, and ISRO, and the Chinese Space Agency. These are the countries majorly involved in many of these activities. And all of you know about, probably know about Hubble Space Telescope, which is in the orbit for past 30 years, and which had, very fascinating discoveries made. And also, it had several servicing missions, in the sense astronauts have gone to the Hubble, Hubble orbit, and serviced the telescope. So they replace the mirror, replace the instruments, etc. So that is the kind of telescope they have built. And then the recent JWST, that is James Webb Telescope. They have spent more than $10 billion, which is about 70 lakh crores, and they spent more than 20 years of making. So this has been flown, and it has been put in L1 orbit. So I'm sure in coming days you will hear a lot about this JWST, science from JWST, and probably I'm not sure whether you had any talk in this your creative team. So with these kind of missions, what is the motivation? Because when you spend several $1 billion or rupees, and also several missions, such missions, so what is the motivation? And it is this the exploration nature of human beings. You all know, the humans have evolved to this level is simply because of his exploratory nature that is there inherently in him. So, what is the exploration? What he wants to, when we look at our surroundings and we want to know everything about that, like that, when you look at the sky, you want to know everything about what the objects in the sky, and like that, when you put whole problem in a nutshell, we want to know what is the origin of this universe and our own existence, our Earth, existence of the Earth, origin of Earth, and uh, its ultimate fate, and then the laws governing the universe. The physical laws which govern this universe, how the planets move, how the stars give energy. So, what is the physics? What are the laws which govern the various working of these objects, and ultimate fate of the universe? In a nutshell, we can put our the curiosity, the questions into these three aspects. And how we do that? So, to understand this, we start studying everything around us. We study solar systems, that is sun and several planets, and then other celestial objects like stars. Then we have galaxies, we have nebula where the stars or planets are born, and then the globular clusters, which are special, special set of objects, a group of stars which you see. And then the compact objects, what are called compact objects like white dwarfs, neutron stars, black holes, and the extreme energetic sources like active galactic nuclei and binary stars. These are the some of the the objects which we see in sky, and we want to study each of these. We want to understand the physics of each of these, and so from that we put the puzzle pieces to understand the larger question of the universe, about the universe. So, the whole story starts, the modern astronomy. I will stick to the modern astronomy. Starts with the invention of telescope in 1608. So many people think that it is invented by Galileo. It is not correct actually. It's invented by Hans Lippershey. He's a Dutch optician, and accidentally when he put the lenses together, he saw the objects nearer. So that he reports, and from there, Galileo, he hears that, and he makes his own telescope. And first time he looks at the sky. So the revolution begins, the change begins from that. So he looks at the sky. If you see in this picture, he looks at the moon and looks at all the craters and mountains, craters. So he first time he says that moon actually, otherwise it was believed that it's all of ocean. Moon has ocean, water, etc. But he says that it's mountains and craters. And also the most important thing he does is with the Jupiter and its moon. He looks at Jupiter and he notices that Jupiter has moons going around Jupiter. And if you think of it, it's the most important discovery made, because that has changed our whole understanding of the working of planetary systems, because that has triggered a whole lot of observation. People days together observed the sky and studied these planets, and especially we must mention that Tycho Brahe is the one who collects enormous amount of data of these planetary movements. And looking at this data, uh, it is Kepler who comes up with the empirical laws, the Kepler's laws of motion, where the three laws of motion, where he describes how the planets move around. So since then, we have Newton who explains why planets stay in their orbit. He brings in gravitational law, and he explains that. So with all these work, we know that we know completely about the planets, how they move, etc. And today we know that its impact of this discovery. All our satellites are based on this principle. Our artificial satellites, which you make and send to space, and which is used for varieties of applications, both societal applications and scientific exploration. We know that they all work based on these principles, and we were able to build these satellites based on these principles. So we have first instrument, that is telescope, made by Lippershey, used by Galileo. That has given us a foothold on these. Basically, it has given us a major tool to study these. Then coming to telescopes, and we started exploring further, and looking at fainter and fainter objects, we realized that we need larger and larger telescopes. So these telescopes are established all over the place, many places, like especially the places which are much higher in the to sea level, and also which is uninhabited, that is not really polluted area. So we have several ground-based telescopes as large as I think the largest telescope is of about 10 meter dia, 10.5 meter dia. So lot of such telescopes have been established in many places. Mauna Kea is a place near Hawaii. Hawaii, it is an island, and several countries have established their own telescope bases there. And then in India, even in India, we have telescopes at Hanley and Nainital and Kavalur. So like that, several telescopes have been established. I think in India, we have the largest telescope is about 3 meter near Nainital. So like this, several telescopes have been established for ground-based observatory. So if you can build this large ground-based observatory, then why do we have to go to space? That is the question. So especially when we spend so much money, etc. And we have atmosphere surrounding us. So this atmosphere affects definitely our seeing. When we see the star, we see stars twinkling, for example. Basically, we all know that stars don't twinkle otherwise. The twinkling is due to the atmospheric effect. The atmosphere around the Earth is constantly turbulent, and because of that, the light refraction, the angle of refraction keeps changing. So you see stars twinkling. So that is not good for us to study the object, because atmosphere has affected. In addition to that, atmosphere has a lot of absorption happening there. And another thing in the meantime, that the objects, the celestial objects, they emit in different wavelengths. So for example, sun's surface temperature is about 5,800 Kelvin. Sun emits mostly invisible and extended to other regions. Whereas if you go to still higher temperature stars, they emit in higher energy or higher frequency, like in X-rays, ultraviolet and X-rays. So like that, we have cooler object will emit in infrared or radio, etc. So other microwave, etc. So that means in order to study these objects, because we want to study everything in the universe, then only you will be able to get the complete picture, and probably get to the bottom of the universe and its creation. So we want to study everything. That means the atmosphere has to allow all these rays to come onto the Earth. But there is a limitation, because atmosphere stops X-rays and gamma rays, thankfully. Otherwise, we all will not be surviving. So here this picture shows that actually. And atmosphere allows visible light, with the, but nevertheless, as we discussed, you have this turbulence effect. Then in infrared here, you have a lot of absorption lines because of the species of the atmospheric species. Then similarly, some of the infrared is not reaching the Earth. Similarly, radio wave, particular wave band reaches, and some more don't reach. So that means we have to go to space. Whether it reaches or not reaches, we have to go to space to have the most effective observation and most faithful observation. So because of this multi-wavelength observation requirement, and also to remove the atmospheric effect, we go to space. And when we look at multi-wavelength band, here there is an example, Crab Nebula. So if you see in the radio, you can see the picture in radio and far UV and in optical and in X-ray. You can see how each one shows different aspects of the same source. So it's a very important, once again, to uh, study this in a multivalent regime. And the same thing, the two pictures of the same part region of the sky, one in optical light, in one another in X-rays. You can see that there are a lot more invisible to our eyes sources, or invisible to through visible camera. So obviously, it is important to study all the wavelength. So now once we know the motivation what we have, we know why we have to go to space. Once we have all these, then the techniques. What are the techniques used? So while it looks very technical, I will try to make it very general. And the technique used, because all these are remote objects, they are in light years, several light years, millions, billion light years away. So you can, obviously, you have to, the only way you can do is remote sensing, because you constantly get light from them, light of any wavelength. So we have to have remote sensing instruments. Instruments here look at those objects and create image or characterize them from that distance. And also, if you are going for planetary studies, if you are in an orbit, going around the orbit, again, you do remote sensing of the surface of the planet. So there are two types also there, active and passive remote sensing. And active remote sensing is where we use a source which illuminates or which excites the target, and then you get the resultant reflecting or resultant signal back. And passive is you don't use anything, either objects emit on their own due to the physics of it or temperature, etc. So we have two types of remote sensing, active and passive remote sensing. And for example of active remote sensing is like the radar imaging. For example, we have it in Chandrayaan also, synthetic aperture radar instruments, etc. So those are the active instruments. And the what you do in remote sensing, we study the light. The light is the only thing which is coming from these sources, and we study them. What we study their energy. The study of energy is called spectroscopy, and we study arrival direction, means the from which point, which place it is coming. If you have a larger extended source, or from larger sky, we know. So that is nothing but imaging. You take the photography. The photographs tell you basically each point what is the reflected light, and the time of arrival. It is called timing studies. And the state of polarization. What is the polarization state of the light you are getting. So if you talk to any of the astrophysics person, astronomers, it is any of these techniques or all of these techniques or combination of these techniques they all study. So that becomes the major part of the astronomy. You study the property of the photon or the light coming from these sources. Quickly we'll look into these four techniques. These are the techniques used. And the spectroscopy, we know what is spectroscopy is all about. And the spectrum is the distribution of light with respect to its wavelength or frequency or energy. And the first Newton shows the spectrum using prism in front of sunlight, and in front of white light, he shows the colored spectrum. And after that, Joseph Fraunhofer, he does more detailed study, a telescope and a prism in front of sun, and he gets sun spectrum here, in 1850, which has some very specific features. You can see some lines, dark lines. So this, however, he did not explain that. It was explained further by Kirchhoff and Bunsen. So both of them, together during their experiments, in the laboratory, they find that these features come from either the absorption or emission. If you see here, the light source through prism, you get a continuous spectrum. And if there is a hot gas means obviously some species. So that emission will have some emission lines. Instead of continuous spectrum, you have emission lines. So those emission lines are, we call them as, fingerprint of that hot gas. They are characteristics, specific characteristic of that the source. And similarly, if you have a source and if you have something in between, which is again some species, say, let's say gas species, it absorbs. So you have continuous spectrum. Some lines are absorbed by this species. So this is the basics of the emission and absorption spectrum. So Kirchhoff and Bunsen explained that, and suddenly they realized, okay, this is the basis in which we start understanding the stars. Okay, sun has these elements. Sun has helium. I mean hydrogen elements, helium. So these elements can be found out. So this is where the beginning of the astrophysics starts, from the study of spectroscopy. And some more examples of the what you do with the spectrum. And you, of course, you study the elements present in the stars. And similarly on the planets also, there are different techniques to understand the elements, the surface elements, the kind of rocks or minerals which is made of. And then another thing, it is, this spectroscopy is done in across all the wavelengths. It is not just visible. We do it in X-rays, we do it in IR, etc. And also spectrum also gives us the information about the temperature of the object. We know black body radiation. So temperature gives you the spectral property, the peak wavelength, and how the spectrum is distributed. And also another very big thing with the done with the spectroscopy is so what is this screen has some, hello?
Yeah, you can. I think you can. Madhuri, can you help? I mean,
Is this from my screen? There is some line and
no.
Sir.
You have to disable that annotation.
Yes, sir.
who I have to do?
Yeah.
Sir, you have to do in your system, sir.
I don't know. It has come suddenly. One sec.
Go to previous slide and come back. It will disappear, but you have to disable annotation. You please continue. It will not trouble you.
That is true, but the slides are also not moving.
Share and unshare, sir.
I will do that once.
Start it,
Okay.
sir. Please.
Yeah.
Please.
Yes, sir.
Right.
Sir, is it okay, sir?
No, it is not. Just give me. Sorry. just give me just a second. Can you see now?
Yes, sir.
Oh,
Yes, sir.
It is visible
okay.
now.
Okay, right. So the spectroscopy has given another, using spectroscopy, we know the universe is expanding. So this expanding universe, first detected by Edwin Hubble when he looked at the galaxy outside our galaxy. That is because initially we knew only the Milky Way is the only galaxy, but once we understood that there are more galaxies outside. So when he looked at galaxy and looked at its spectrum, we are seeing that the characteristic lines are shifted. What you would see from the spectrum, lines are shifted. So this red shifting has been explained, by the expanding universe. So that is, if the universe is moving away from you, the spectrum shifts towards red, and if it is coming towards you, it should, if any object coming towards you, the wavelength shift towards the higher wavelength, that is towards blue. Rather smaller wavelength, that is towards blue. So we have this red shift observed in the spectrum. I think there is some other thing happening. Somebody's.
Yes, sir. I will remove them, sir.
No, just on the right corner, you have options. More some
I'm not doing
disable.
anything, Srinath. Probably it is somebody else is doing.
No, that's when they are touching the screen, no, that will come. This is all mobile, no. Everybody will be attending mobile. On the
Okay.
right corner, the top, there is a settings for you, more options.
For me?
Yeah, in that one,
Yes,
disable
sir.
annotation.
So any of you can do that from your end? Okay. 1 minute.
No, sir. You have to do, sir, in your screen.
Okay. I'm just trying to see where. Okay, more here.
Disable annotations.
Annotation for others. Okay.
Okay.
I
No,
did
it will
that.
not.
Okay.
Yeah.
Okay. Fine.
Yeah.
Right. Okay. So
Go back, maybe share and unshare it. It will be right. Because it's all mobile, they will be touching there. So it will.
Okay. So it's all right now?
Yes, sir. It is
Yeah,
visible now. You can continue, sir.
Yeah. Sorry for this glitch.
It's okay, sir.
Okay. So we see. From spectrum, you have understood that the universe is expanding, and the expansion rate also is estimated further on. So like that, and also the spectrum, recently this same spectroscopy is used in detecting the exoplanets, that is extrasolar planets, the planets outside our solar system, what is called radial velocity method, where a planet which is you can see on the left side, a planet going around a star, and if the planet is big enough, it will create enough wobble for the star, which will show this shift in its spectrum. Because of wobble, we'll have continuous red and blue shift happening. So with this, you can detect the planets. And however, this is possible only if you have what is called edge-on view, just like what you see on the left side. On the right side, if the situation is like, if it is like this, you will not be able to do that. So that's about spectroscopy. Then the next technique is imaging photography. And you can see on the left hand side, the very first photography image of Orion Nebula, and it is in 1880. And after exposure for 137 minutes. And on the right side, you see the modern CCD based, that is charge coupled device, is a sensor, CCD based image. So we have progressed so much using the modern instruments. And the another technique which we discussed, that is the timing. In timing, you measure the flux variation with time. So this can study, this is used for studying the source variability. That is the source emission. It varies, certain times it varies, it suddenly erupts, or it gives a periodic feature. So with these kind of studies, that is with the timing studies, you can understand many aspects of the sources. So for example, you have a binary star orbit where it will have a period, so you can estimate the period of the star. And then you have a supernova explosion, so you will have the sudden burst in its intensity. So you will have brightness increased and decreased. So with this, the kind of feature, with this kind of the kind of profile it shows, one can understand the type of supernova explosion, etc. So the timing study also is a very important technique used. And also timing study is used. This is another technique used in exoplanet detection. That is, we call it as transit method. Here in this picture, if you see, you have a star and you have a planet. Planet, 1, 2, 3. That is planet position 1, 2, 3. When you have planet moving in front of star, when it goes around the orbit, you see the brightness also changing suddenly. The brightness of the star, planets don't have their own light. When you look at the visible light coming from star, you will have its brightness going down and coming up again. So with this method, you determine, okay, there is a planet, and the amount of dip, etc., will can give you further, and also the period of this dip will give you the more information on the planet, its mass, its orbital velocity, and other aspects. And the fourth technique which we discussed is polarimetry. So this is the picture of sunspot. So I am sure many of you are aware of this kind of sunspot pictures, very high resolution sunspot. And so here you can see some, the very fine features, some elongated features, etc. And when you look at closely this, and when you study the light coming from this region of the sun, you know that it is nothing but the high magnetic field orientation. So you can see that this is in fact the magnetic field orientation which causes this. And the magnetic field is responsible for this structure. And also by studying polarization, you can determine the magnetic field. And also process identification means the polarization happens due to scattering. Polarization can happen due to the physics itself, like synchrotron emission, etc. So you can understand by studying polarization, you can understand what actually is the physics behind this polarized light. So these are four techniques which are typically used by astrophysicists, and these are remote sensing techniques. And then the space science. It is not when you talk about space science, it's not just that studying of stars, galaxies. We also study the planets which are close by, and the farther planets and interplanetary space, etc. So there are other techniques used in many of these missions, and just giving you few of them, example of few of them. And these are called direct sensing. They are also called as contact instruments, because instruments basically, they measure the immediate surrounding of that. So like, for example, the gas or the particle or magnetic field, etc. But they will not know, or they may not really tell you about the source, which source it is from, etc., without help of other studies. So these are called direct sensing. So direct sensing, we have things like low energy particle detectors, high energy particle detectors, and the plasma detectors. And then we have magnetometers, and there are dust detectors, which are used in many of the mission, like the Cassini, etc. So, and then mass spectrometers are widely used to uh, to study the neutral and molecular species uh, around, near the planets. So these are widely used in planetary and robotic exploration. So these are examples of direct some of the direct sensing methods. Not limited to this, one can come up with any new technique to study some aspects of any of these planets. So that is about the techniques. Then what are the challenges then? So we know all these techniques are used now, and what are the challenges? So to build these instruments, it's extremely challenging because there are several aspects involved. So the requirements are really, very, very demanding. The first requirement is high sensitivity instruments. The sensitivity, you all know, the smallest signal an instrument can detect, or the uh, against all the background, etc. So the sensitivity of the instruments has to be very high, and the instrument will typically have optics, detectors, and various other instrument systems like electronic system, etc. So all these aspects should be built such that you are able to really, pick out the smallest signal you are getting. So we have to build them with the very high sensitivity features. And then there are other challenges in mission, etc., orbits, etc. I may not talk much on those things today. And then the instrument stability, yeah, even the once you have high sensitivity instruments, and you are looking at a very small part of sky for various observations, the stability is very important. So while both the instrument has to be configured, as well as the support instruments for the satellites, there are, because the platform stability is ensured by various other systems, other sensors and actuators. They have to be built to, to very demanding requirement. And then deep space missions like Voyager, etc., science missions, they have other challenges, like you have to reach those spaces with the, spaces. You have to achieve those greater distance with the fuel efficiency, etc. Again, I will not talk much on that. So a little bit we'll talk on this high sensitivity instruments. So a remote sensing satellite, for example, this is a picture of Chandra satellite. Chandra is a NASA spacecraft, which is an X-ray observatory. So it orbits around the Earth, but looks at the sky to look at the X-ray sources in the sky. And if you look at the major part of the spacecraft is this instrument is the optics. Then we have detectors, and then we have electronics, and other satellite aspects are of course there. And why we need big optics, etc. So we'll just come in a minute there. And the high sensitivity requirement is there because you have sources which are very far, and very far sources will be very faint. And the classic inverse square law, the intensity reduces as a square of the distance reduces by 4. So uh, so you have the intensity reducing drastically as the source is further the source, the intensity is really reducing to a very small. So that means, as this picture says, so the first A faint, um, if the same number of same amount of light, if you want to collect, you have to have large area in the second thing. So with the same area A, you cannot collect enough light. So you have to have large area. So that's where that's how you increase the sensitivity, because sensitivity is increased by increasing the area and also increasing the observing time. But of course, there are, just observing time, if you increase, you cannot, because there are other things also increases. You have background also increased, etc. And then the reduced background. What is background? So when you look at the source, you want to look at only the source. You don't want to look at any other nearby source or the etc. So if you are looking at a source in a X-ray, let's say X-ray, then you don't want any other X-ray coming from any other source. So those are unwanted. They are background for you. So you have to see how the background is reduced, whether you can reduce by having a tighter FOV, and then you can increase the area of the optics, and small detector, the background due to detector, the detector background is reduced, and you have source strength increased by increasing the optics area, that is by collecting by having a large collecting area. So with these techniques we can increase the sensitivity. So here you can see the optics. We talked about optics. Optics is the one of the best method to improve the sensitivity. You can go for larger and larger optics, as and then another thing is, for imaging, you obviously need optics, because without optics you will not know the photon coming from which point of the object. So you will not get the image. So you need to have optics for imaging, and also large area collection, but with small detector. So the lens system is one such optics, and a lot of challenges here when you go for more and more sophisticated optics, because large lens system you should have, and the lens quality has to be maintained. Quality in the sense that these lenses have to be properly, ground. Ground means polished and shaped. The shape and polishing is very important. These are all technology challenges. So the optics and optics for visible light is different from IR, and for X-ray it is totally different. For X-ray you will have grazing incidence. You cannot bend light or X-ray in the optics which are similar to the ones which used for visible light. So you have to have a lot of optics development catering to variety of these requirements. And then there are also other techniques used, the mechanical collimators. These are much simpler, where you restrict the sky region of the sky, but you cannot do fine imaging with this. But nevertheless, you can restrict the field of view and focus in that small region and get the data. And then coded mask, where you have a mask which is this is mainly used for X-rays. Where you have mask which is coded to a pattern. And for example, in this picture, you have red star, which is red and blue. The red star will have a particular shadow pattern, and blue star will have another shadow pattern because of the location of the star with respect to the mask and the angle which is making. So looking at this pattern, you can derive back the position of the star. So like this, lot of technologies exist, and continuous effort is there in making these optics better and better. There is a lot of effort going into X-ray optics making and also normal optics making. And this I'll skip, because already we discussed. And we need large telescope, because the light collecting power increases, and resolving power is there also improves, and sensitivity of the telescope also improves. And then once you have optics, then you have detectors and electronics. So these also have a lot of challenges, because all these things should have very low noise. And when you go to space, we will have radiation. There is particle radiation in space. This radiation will constantly hit these instruments, and probably damage the electronics components or the detector system. So you should build your instrument or you should choose your components which are radiation tolerant. And then there is the thermal control is another challenge when you design the system. Well, for example, James Webb Telescope, I don't have details today on that, but you all would have heard elsewhere about the challenging aspects in building James Webb Telescope, where a lot of thermal control has gone into. There is a huge shield developed, and then the whole orbit is put it in Lagrangian orbit so that you don't have thermal background much, because it is basically IR. It's concentrating in IR, and it is the thermal radiation which will affect this IR source sensing. So a lot of thermal control goes into, and then we have deployment mechanisms. Again, when you go for larger and larger optics, etc., for example, the optics cannot be, optics has to be placed in a particular location. If say, let's say X-ray optics requires a long focal length, say 5 meter, 10 meter, that kind of focal length. And how you achieve that? Because if you have a fixed optics, you cannot put it in a rocket and launch. So the rocket will have limited space to accommodate the satellite. So you have deployment mechanism. The optics is held, and after releasing in space, the optics is released. So deployment mechanisms. All these things are very, very involved technology, very high technology involved in these things, because they have to be space qualified, etc. And those things have to be developed for each mission, each requirement. It is not that one mechanism, probably principle can be same, but the requirement will be different, the mass will be different, and the stiffness, etc., required for the structure may be different. So a lot of challenges in mechanism development. And finally, we have to see these two things, low mass and low power. That also has to be met, especially the planetary mission, etc. You will have multiple payloads, and the payload mass has to be kept very minimum, so that uh, you can have very efficient, the cost efficiency and performance efficiency ensured. So these are challenges in this system design, instrument design. And the in that low noise, a lot of work for electronic system here. The electronics signal, I mean the noise has to be very, very minimum. For example, here if you see on the leftmost, you have noise, and the second one signal, and when you have them together, you have noise merged in signal. And the light, as I said, the light or the energy, smallest energy you have to detect, the smallest amount of intensity you have to detect. That means the noise, the background noise, electronic noise has to be minimum. So this is a challenge. So one has to very carefully design the electronic system, the PCB layout, the component selection, etc. Matter a lot. And whole instrumentation, that is how you put the detector and electronics together. All these things will decide this ability to have a very good less noise system. And coming to detectors, varieties of detectors are there. We have optical detectors, IR detectors, UV detectors, and X-ray, gamma ray detectors. So varieties of detectors are there. So each mission, if it is X-ray mission, if it is IR mission, you have to choose appropriate detector, looking at the wavelength, looking at the resolution required, and looking at the area required. So a lot of these factors decide which detector we choose. Once you choose the detector, electronic system has to be developed. And all these detectors are, any of these, either semiconductor detectors, they are like CCD, or diode, PN diode, you have PN diode principle based detectors, like IN diode, PIN diode detectors. And then gas field detectors, maybe some of you have heard of proportional counters, etc. So the detector based on those principles. Then scintillation detectors. So all these are very different types of detectors. So one has to choose appropriate detectors, configure them for the job to be done. And after making the instrument, I will not dwell too much onto these things because it becomes too technical then. So the calibration of the instrument is very, very important. You have built the instrument, you are looking at the source, but you want to know what you're looking at is what you're looking and inferring is the correct thing. So you have to calibrate. That means calibration here is your instrument, its response or how it behaves for a given for a given condition. That is, for a particular temperature, for a particular energy, what is your detector shows? What is that your detector shows? So it may not see a single energy is like a, ideally it's a delta peak, which is never a delta peak. So it will have a Gaussian peak. But the detector will have its own internal way of functioning. So it may be Gaussian plus additional features. So you have to properly characterize or calibrate these things so that when you really see a source, you are able to infer it correctly. So you have to do a lot of ground calibration, and then you have to do calibration in space also. And of course, there are other theoretical models also you have to develop based on the known physics of the functioning of your instrument. So with all this activity, calibration is the most important, one of the most important activity of making a instrument, building, and getting the data out of it. So calibration activity is a very important thing. And then you have to do also study the background. So your instrument will sense everything what comes its way. So it will sense the source, also it will sense the background. So background also will have lot of things which is similar to source. So any signal which is other than source from the source is called background. And there will be instrument background also. See, ideally an instrument should give a signal when there is a external stimulant hits that. So like, for example, X-ray photon hits that and you get a signal. But because of temperature, semiconductor detector, for example, it will have its own what is called dark current. So these are all coming to background. So we have to properly analyze, understand, and then we have generally in sky you have galactic cosmic rays and cosmic X-ray background. All these things are there. So all these things have to be properly modeled, because your instrument to instrument, this background will be looking different, because you have a lot of materials around these instruments. All those things will affect the final background what you see with the instrument. So these are all a lot of involved activity in making instrument. So that is about the generally building the instrument. But after building instrument, as I said, even in a mission, we have a lot of challenges. Like you have to choose the right orbit, and then to do the modern astronomy, you have to have very sophisticated satellite platform. So, like for example, this picture, if you see here, the background picture is a Hubble deep field image. Hubble Deep Field Image, as you can see here, is the farthest object which we have seen. That is about 13.3 billion light years away. So that is about 5 million, rather 500 million years after the Big Bang happened. So this is a very important image, because you are starting to understand the early universe. By directly you are able to observe the early universe, the early galaxy formation, the homogeneity of the universe, etc. So these gives a lot of further tool for you to understand the early universe and origin of the universe. And here, this image could be recorded because of the kind of platform stability and pointing accuracy what Hubble has. Hubble has lot of sensors mounted, many sensors and actuators mounted all around the telescope, and its pointing accuracy achieved is 0.007 arc second. That's the kind of accuracy it has achieved. And this particular place is such a small place in the sky, which is because otherwise you will have the stars which are in front. So you have to see through these stars, means you have to see the blank space between stars. So we need this kind of pointing accuracy, etc. And this particular image is exposed for 23 days I mean, cumulative exposure is about 23 days over 10 years. Uh, so over 10 years, 23 days, the small area of the space is observed and this image is captured. So the modern astronomy definitely requires a very, very sophisticated instruments, new instruments, etc. And so I'm almost coming to end of my talk. And so this is the kind of requirement. And after Hubble, you all know that the recent spacecraft which has been flown, that is James Webb Telescope. As you can see, the thermal shield here, you can see the large foils, which are nothing but thermal shield, and the mirrors here. It's I think about 6 meters total diameter after the mirror deployment. And these mirrors were folded. As I said, the mechanism, the unfolding mechanism has to be developed. They have been developed. And post deployment, the alignment accuracy has to be ensured so that you have a perfect sharp image. So these are the future challenges, they have met and they have launched, and we are looking forward to really a very exciting time with these very, very sophisticated instruments and satellites built. And with that, you can see still with the Hubble, it is expected that we can see still early universe, the Hubble, sorry, with the James Webb, because Hubble could see up to, 13.3 billion years old images, whereas James Webb can see further beyond, which have been, from which the light has been redshift, right? Light is redshifted because it is farther. So which is beyond Hubble's sensitivity. So James Webb is sensitive to that. So we have exciting time ahead. And with that, I'm just stopping my presentation. Thank you for your attention.
Sai Madhuri, you can unmute.
Thank you. Thank you, sir. It will be curious to know about space, but by this session, we are curious about space instruments also, sir. Thank you, sir.
Yeah, thank you.
So, with your permission, can we ask questions?
Yes, yes. I will try to answer. Yeah.
Sai Madhuri, first take it in chat box.
Okay, sir. Sir, here is a question from Vinay.
Yeah.
Sir, particularly how far
practically,
in time?
Practically how far in time?
Practically how far in time? Yes, sir. We can see how
near can we practically go to Big Bang event. Okay. Okay. How far? See, the thing is, now we know that universe is 13.7 billion years old. So 13.7 billion years old means it would have now, after the Big Bang, it would have expanded. So, but light, we will be able to see the light which has traveled since then to now. That is about 13.7 billion years. But when you see that, the object is much farther. So that way, the definition of that, object is much farther at this moment. What you are seeing today has traveled further, 13 further beyond, and the universe is expanding, and the expansion rate is higher as the distance is larger. So practically, I think some number is there about 90 billion light years is what I understand. I think I remember, but it is something like that. Yeah, but there is a limit what we can see. So have I answered somewhat?
The winner has no speaker. I think he's satisfied.
Okay, amazing. Even if one star in our galaxy comes in point of view, it may block the deep field image. Okay, I think is just expressing his.
He's responding,
yeah,
sir.
Yeah, responding. Yeah.
Somebody has raised hand. Sai Madhuri, please call them and unmute.
H.H. Patil.
Yeah.
Patil, you can ask, I think. Yes,
hello,
you
sir.
can ask now.
Yeah.
You can introduce and ask, sir.
Hello, sir.
Hello. Yes, sir. Patil, sir.
Yeah. Am I audible?
Yes, yes.
Hello. Thank you for the good lecture, sir. It is very happy to hear the full lecture.
Yeah,
Just
thank
I
you.
would like to have some words like that. Space explosion, space whatever you are exploring space, now sir, deep
Yes.
space.
Yeah.
That is the only work that I feel like it is very the goodest thing that we human are doing. Like we all are humans are doing something to get something back. But this space explorer thing also are just to know things.
Yeah.
That is that how the universe is made up of.
Yes,
It is
yes.
it is I think it is a truest thing we have to know that from our single cell to our whole body and
Yes.
that outside universe.
Yes.
Just knowing this thing is a very good thing, sir.
Yeah.
That NASA and ISRO things are doing. That is the coolest thing we are doing, sir.
Yeah.
Like I'd like to ask one question, sir. One interesting question I'd like to ask that I have to know.
Yes.
We are telling this object is this year's this distance away, no, sir.
Yes,
But
yes.
just by getting the light,
Yeah.
how will we come to know this light has traveled this much distance? Like we will say it is some light years away. How will we come to know, sir, this light has traveled this much distance?
Okay. Okay. See, hello.
Yes, sir. Yes.
Okay, okay. So the distance of stars, that's what you are asking. So there are several techniques used for measuring the distance. Of course, one is parallax method, but that is for nearby stars. Then there is another method. I'm not fully expert in that. Cepheid stars, which show the varying intensity. With that, they measure the distance. And then third one is this redshift itself. It's a method to look at the distance. And also the looking at the spectrum, the apparent magnitude of the spectrum. So with that also one can understand the distance. So there are several techniques used.
Okay, sir.
Yeah. Somebody wants to add?
Thank you, sir. Then Vismaya. Vismaya? Hello, Vismaya?
Go to next speaker. Next question. Next question.
Next, Pranavi. Pranavi? Are you able to mute yourself? Or not?
Maybe you have to unmute them, Sai Madhuri.
I did, sir.
Or else read the question from chat box.
I did, sir. Pranavi, can you ask now?
Yes,
Ask.
sir, I saw a video from YouTube that is from the sun there is a solar rays that is like a disaster that will disaster our world in 11 years. That is real.
I don't think so. 11 years. What video you have seen, Pranavi?
In YouTube a video.
YouTube video. I don't know what you are referring to, but nothing will happen to sun and for next several billion years, 4-5 billion years, and also nothing is expected which will destroy whatever you are talking about. That's what you said, no? Disaster is what you said.
Yes.
So I don't think there is anything like that. But nevertheless, sun every now and then sun becomes very active and gives out a lot of energy out. So which can okay, I think you are trying to say that sun has a 11-year cycle. Sun becomes more active every once in 11 years in that cycle. So when sun is very active, is that what you are saying? Okay, let me answer that. So every once in 11 years, sun becomes active and gives out a lot of energies in the bursts. So those whatever energy it spews out, It can be high energy, very high energy, and it is a danger potential danger to many of our space systems. Say, for example, satellites. There are satellites which can get damaged with these kind of energy released from sun. So that can happen. But I think that's what I understand from your question. Is that correct? What you said is correct?
Yes, sir.
Okay. So the every once in 11 years it will happen. But yeah, it will not become disaster to our earth or like that. But there are a lot of studies going on how this sun's 11-year cycle affects the space weather. Space weather means the environment in space, and how this space weather is. Hello.
Yes,
Yeah.
sir. It will affect our earth.
How the space weather will affect our weather, those studies are all going on, but there is no known big danger as such to the earth directly, if I can say so. Yeah.
Sai Madhuri, next question.
Pranavi, can you ask now? Pranavi? Shreya? Shreya, can you
Probably you may have
unmute
to
yourself?
unmute them.
Sir,
Okay.
So by the way, I am not an astrophysicist, so I'm basically instrument scientist. So yeah, that's a disclaimer I am putting.
So if you have some
Pranavi?
question which needs to be answered, he can also take part, sir. Girish, you are open to be the question.
Yes, Girish can join. My friend Girish is there. He is a astrophysicist.
Yes.
Yeah.
Yes, sir. So good evening. This is Dinesh from Chintamani Government Degree College.
Yes, Dinesh.
So I have a doubt related to the redshift. So only that red color will be taken as a reference, or there could be other colors. There will be absorption of.
Any color. Red is called because see, as we know, in visible light, red is on the longer wavelength, right? Lower energy. So
Yes,
anything,
sir.
even in X-ray, lower energy, when it goes, it is called redshift. So it's just a somehow that name has is stuck because the first observation was happened in visible spectrum.
Yeah. So in the same spectrum, there are other colors whose shift in the other direction. I think I had observed that.
No. And all the colors will shift towards red, means longer wavelength.
Yeah. That was not observing with that spectrum. That is one question. And
you are not observing. Sorry, what is that?
That was not observing with the spectrum what it was got displayed.
I think entire what I was showing all those absorption features, lines, right?
Yes, sir.
So entire it's as I said, it's a fingerprint. Say, let us say hydrogen lines. Hydrogen lines will have several ionization lines.
Exactly.
So that entire set of lines will shift. So I think it has to, but if it is not, I will recheck my slide. And if it is not, definitely it is not true. It's not so. Yeah.
Akash, can I just answer this question?
Yeah,
can I just add on to your whatever your answer?
Sure, please.
Yeah. So as Dr. Radhakrishna is saying all along, so what we use redshift is for actually measuring distances. Anything which is moving away from us. So anything which is moving away from us will be redshifted, means it will lose energy. When the photon loses its energy, so you know that hc by lambda, so the lambda will increase. So that's why if you take our rainbow, you know that red is at the other end, lower energy end, and blue and other things are at the higher energy end. So once the energy becomes lower and lower, we call it as it's moving towards red. So that's why the name redshift. Okay, so this is for everything which is moving away from us. Similarly, we have blue shift also, and we have P Cygni profile, where you can see in the same spectrum both redshift and blue shift. Means some of the items will be moving away from us and some of them will be moving towards us. We will see what we call it as P Cygni profile. In a same spectrum, you can get both red and blue. Now the next question, whatever you asked and whatever Radhakrishna answered almost correctly, is that with one single line, it will become very, very tough to identify what exactly is the redshift, because you know that there is one line at 100 angstroms, it might have become 110. Now we don't know whether 100 has become 110 or 90 has become 110. Right? There's a possibility of both. That's why what we use it as a comb. So we see how much each one is moving. So if we take 3 lines, all the 3 lines moving with different velocities will be almost impossible. So by actually using more than 2-3 lines, we can actually identify exact redshift. I hope I have answered your question.
Yes. That intensity will be very, very less, right? So,
which intensity you're talking about?
This particular colors, when you take the intensity
lines
of these colors.
You mean to say lines?
Yeah, intensity
So
will depend on
that we can
the
overcome by
distance.
actually observing for a very, very long time.
Yeah.
Okay. And
another
question.
And another thing I just wanted to ask, I wanted to tell, is that we don't just use lines for actually identifying redshift and blue shift. What we do is we take a broadband filters. So we actually observe in not one of very, very narrow lines, but very, very broadband. And we take the difference between multiple bands. Some people call it as UBV, where we use very close to blue, ultraviolet, B, and V colors with the defined different line, this one spectra. So that shape from the U minus B divided by B minus V tells us what is the redshift. So in that way, intensity can be, even the fainter ones can be measured in that way. Hubble mainly uses that for identifying the distances.
And another question related to the sunspots. Sunspot is observing because of the magnetic flux or
sunspot is associated with magnetic field. Yeah.
Yes, sir. So it is maybe because of more activity at that place. Is that?
Yeah, during sun activity, you see more of sunspots, and it is related, sun activity and sunspot. Basically, the creation and synthesis and creation and evolution of sunspot is called, the solar activity. That is the one which finally, results in solar flares, etc.
Yeah. Similarly, we have like a Bermuda Triangle and all on the Earth also. This is also, there is some magnetic.
See, Bermuda Triangle, I have no idea what exactly is the issue, because still I think nobody knows about it. But there is something called magnetic field. Yeah, that's what they say. But there is something called magnetic field anomaly near close to that region. That is called South Atlantic anomaly, where the magnetic field is much closer to Earth. So that is there. But the correlation of Bermuda Triangle to that, I am not aware of that. Actually.
Okay. And these sunspots are keep on changing, right, sir?
Yes, they keep on changing. Yes.
Dinesh, before you go to the sunspot, so since you mentioned about Bermuda Triangle, so Professor H. Narasimhaiah has actually edited one book called Science, Non-Science and Paranormal. So he talks about how this Bermuda Triangle is just a myth. See, the number of accidents occurring in that Bermuda Triangle is almost commensurate with any other place. But we have selective amnesia or selective memory. So we remember the ones which are associated with the Bermuda Triangle, and we try to give more importance to that. And hence people say that Bermuda Triangle is some strange place. But he has proved, and many scientists have proved, that the number of accidents happening in that area is almost same as the rate, is almost same as any other place also. So this is almost like 20-25-year-old book, Science, Non-Science and Paranormal. If you check that, you can clearly see that time itself they have actually explained what Bermuda Triangle is and other details.
No. Sir has pointed another one is that South Atlantic anomaly.
No, South Atlantic anomaly is Sun's rotation axis and Sun's magnetic axis are not aligned. So at one point, magnetic axis comes closer to Earth's atmosphere compared to other places. So that is what he is talking, and this point happens to be over the South Atlantic, and that's what he meant by South Atlantic anomaly. Okay, but this
that
magnetic
correlation is
field,
never there. Yeah.
yeah. So it is not coinciding with that particular place. We do have problems with South Atlantic anomaly. That's why we are very much aware of SAA. So Radhakrishna wants to switch off all his instruments whenever it is very near the South Atlantic anomaly, because the charge particle density is very, very high there.
Okay, okay. So now coming to sunspots again, sir. These sunspots keep on changing their places. Why it is happening? Like all over the sun, it will take place, or only at particular places it keeps on observing, something like that.
I'm not
Yes.
solar physicist, but I can tell you that I think it is not
Sometime
understood yet.
also, so that solar questions will be answered.
Yeah,
But
you
still
will
you can
answer. But I think
Yeah.
I guess it is not known yet. So that's
No,
why
no, no.
many of these
Actually,
missions.
we know few things. Okay, so what is
No,
happening is,
whatever he is asking.
no, I'll tell you. So the sunspots are the footprints of magnetic loops. Okay, and these loops usually develop at equator and move towards the pole. So when they are moving over the entire their life, it looks like they are coming up at multiple places. So if you see, majority of them actually starts at the very close to the equator, sun's equator, okay, and moves
Yeah.
towards the pole.
Very nice presentation. Thank you. So
Yeah, thank you.
thank you. Yes.
Thank you, sir. Now, Marzuk can ask the question, I think.
Check the time also. Check with Radhakrishna.
Yeah. What is that?
Time. Radhakrishna will
Yeah,
be
no problem. Another one or two, maybe no problem. We can just try to address. So there is a question. There's some chat box questions are there.
Please take, sir.
No.
Are we able to make a map of universe? Okay, I think the several maps are made. X-ray map, gamma ray map, like that. Map of the universe is made. So and they keep making new maps. That's what I can say. And I think next question is actually for Girish. Would like to know about the payload in AstroSat 2 mission. So I think
Maybe you come to know very soon, sir. Yeah.
yeah. Right now there is nothing about that which is finalized or known. So
yeah,
probably
we'll come to know very soon.
Yeah, right. Maybe. Yeah.
Somebody has raised hand. Sai Madhuri, please allow them.
Sir, Marzuk. I allowed him, sir.
Yeah, Marzuk.
Sir, can you hear me?
Yes.
Yes.
We can hear you.
Sir, what is the shape of the universe? Have they confirmed?
Okay. Okay. Probably if you look at the Big Bang thing, it probably should be spherical. But if you look at the map of the universe, most of the objects are placed in distributed in a plane. But I think it is spherical. Girish, since Girish is there, confidently I am saying this much because he can correct me and tell more.
No, you are saying whatever you are saying is we expect it to be very close to spherical, except for the minor variation in the velocity with which galaxies are moving away from each other. And whatever he said second also is correct, because most of them depict the target sources within our galaxy. So that's why it almost looks like it is very, very flat.
Sai Madhuri, please check it. And if no questions are there, take a concluding signal from Radhakrishna.
Yes, I think no questions more, sir.
Yeah, you can go for thanking.
Yeah.
Okay, thank you. Thank you very much.
Before Sai Madhavi takes over, I would like to thank Radhakrishna. And actually, I did not know that some of the words he used. So whatever that touch, he talked about something where everything is, you have to actually be in situ. I always thought that it is in situ measurements, but he used something like touch measurement.
Direct measurement.
Yeah. So I was not aware of that. So I learned.
Both are used. In situ is also used.
So thank you very much, Radhakrishna. So you touched upon everything from remote sensing to in situ. So it was really nice talk. Thanks a lot from my side.
Venkatesh sir, you can unmute and say. Give 5 minutes, Madhuri. Anybody who wish to say something.
Yes, sir.
Venkatesh sir, please go ahead.
ನಮಸ್ಕಾರ ಸರ್.
Namaskara. Yes,
Basically-
sir. Yes, sir.
ಕೇಳಿಸ್ತಾ
Nice to
ಇದೆಯಾ?
see you. Nice to see you
ನಮಸ್ಕಾರ
here.
sir. Nice to
Yes.
see you. Nice to see you. Very interesting topic you have selected. It is very new to me also. So we used to see by naked eyes the sky, but you have given us initially you have given us a small telescope. Then you have taken us with radio telescope, then X-ray telescope, gamma telescope, and you have given us a lot of sources as well as detectors and challenges for all the design aspects. So it was a wonderful lecture. I'm able to catch many more things from you.
Thank you.
Thanks to the organizers, as well as thank to Radhakrishna sir, Girish sir, Srinath, and whole team. Okay, thank you one and all. Thank you.
Thank you.
My
Venkatesh,
best
sir.
wishes.
Yeah,
Yes.
thank you. See you. Sir.
Anybody in the participant list would like to make 1 minute short brief? You can make. You can unmute yourself. Sai Madhuri, just ask them to unmute.
Yes, sir.
Narahari, Lakshminarayana sir, anybody, just volunteer, 1 or 2 people. Vijayashri, those who can speak. Otherwise, we will be concluding it with the permission of Dr. Radhakrishna. I think maybe Madhuri, Sai Madhuri, may please conclude.
Yes, sir. Thank you so much, Dr. Radhakrishna sir. You made us know many unknown things today. On behalf of the creative team, I would like to thank you so much. Thank you, sir. And I would like to thank Srinath sir for your support. And thank you, Girish sir, for your add-ons. And in the absence of Supriya ma'am, I would like to thank you, ma'am. And I think we can wind up our program.
Yes, thank you. Thank you, Dr. Radhakrishna. Thank you, Girish.
Thank you, Radhakrishna sir.
Thank you all.
We are closing, sir.
Yeah, sure. Bye.
Thank you, sir. Thank you.